Hi folks, in this video I'll talk about alluvial fans and their deposits. Alluvial fans are fan-shaped accumulations of coarse-grained sediment with relatively steep slopes that occur wherever a confined flow spreads out and thins and loses its capacity to carry sediment. Where alluvial fans occur is along mountain fronts, such as this one on the eastern side of Death Valley. Alluvial fans occur here because strong confined flow in channels, such as here and here, spreads out upon reaching the basin floor, and consequently it loses its capacity to carry sediment. The resulting deposit is relatively semicircular, radial, hence the name fan, and has about a constant radius from the point at which the feeder channel exits the mountains. This part of Death Valley is undergoing uplift along a normal fault, and that normal fault approximately lies right at the foot of the mountains here. And that's why we have very steep relief here. The alluvial fans that occur on this side of Death Valley next to that fault are relatively small because the drainage basins that feed them are relatively small. And just to give you a sense of what I mean by small, this is a road here for scale. So we've got one small fan here and a much larger fan here. And the reason that this northern fan is, or this upper fan is small and this fan is much larger is because the drainage basin feeding the lower fan is much larger than the small drainage basin feeding the one on the top. Now if we look across Death Valley to the other side of the basin, we can see the fan that I showed you on the first slide right here, with that road on it. And we're looking across a flat basin floor. And the white sediment there is all evaporites from a dried lake bed. And if we look all the way across the valley here, we can see that flat valley floor ends. And we have a slope leading up to the mountains. And that slope has several feeder channels in it that are feeding individual alluvial fans. And those alluvial fans have grown so large that they have begun to coalesce along the mountain front, forming what's essentially an apron of debris on a fairly steep slope, and this is called a bajada. The alluvial fans on the far side of Death Valley again are much larger because the drainage basins that feed them are much larger, and larger drainage basins can produce more sediment. Okay, alluvial fans typically consist of an inactive area and an active area, or a lobe, where sediment is being deposited. Here the lobe is this lighter colored region, and the inactive surfaces are darker in color due to a form of weathering called desert varnish that occurs in this part of the world. Flows coming from the mountains are eroding the upper fan here. So on either side of this feeder channel you can see dark colored inactive fan surfaces, and if you look carefully right through here you see a little cliff on one side of that feeder channel because of the erosion that's taken place. Below a certain point on the fan, however, this erosion that occurs in the head of the fan transitions into deposition on the lobe. And we could just draw in sort of a line here at which that transition occurs. where you have erosion uphill of that, deposition downhill of that. And this zone is called the intersection point. So if we were to draw a cross section longitudinally through this fan from A to B, and I'll draw that in yellow at the top of this slide. There's A and there's B. We have the fan surface, whether it's inactive or active. The upper part of the fan surface has been incised. So in that feeder canyon, all of this material has been eroded away. And then the lower part of the fan is where deposition is taking place, and so sediment is being deposited in the lobe here. So we have a lobe on the lower part of the fan, a fan head incision at the upper part of the fan, and in between these 2 points where we transition from erosion to deposition is called the intersection point. And if we were to do the same sort of cross section, except now we'll go transverse across the fan from C to D, show you what that looks like. Do it smaller here. It's fairly simple. From C to D at a different scale now, we have a flat basin floor underlying this fan, and then the fan is a mound of sediment, convex upward, that tapers off in 2 directions. Could be tens to hundreds of meters thick depending on the size of the fan, but alluvial fans generally will produce these lensoidal large-scale deposits. So here's an example of that. This is taken from an outcrop in north-central China. The entire mountain that you see here is made of conglomerate, and down at the base of the mountain here you can see a road for scale. And about in the middle of this cliff face, see a relatively horizontal bed that stretches the entirety of the cliff. And if you follow beds above that, you can see that they thicken somewhat. And so this would be the right-hand half of that transverse section of an alluvial fan. And here we're just looking at an ancient alluvial fan that's now been buried and is visible to us in outcrop. Alluvial fans have slopes that range between 1.5 and 24 degrees. The flows that run down them are usually very thin. And that combination of steep gradient, which produces high shear stresses and therefore high velocities, and shallow depth means that clear water flows traveling down an alluvial fan will usually be supercritical or rapid. Most of the bed forms that you would get as a result of that would be anti-dunes, not dunes. And you might see some higher flow regime structures like cyclic steps as well. So this plot is showing you for slope of a surface on the y-axis versus depth on the x-axis, where the boundary lies between supercritical and critical flow. Or sorry, supercritical and subcritical flow. And if you plot where most alluvial fans lie in terms of flow depth and slope, They would lie in this box, and that box would continue all the way up to about 24 degrees of slope. And most of this box lies in the supercritical flow field, and this is basically just a plot showing you that most fan flows are rapid or supercritical. And if you compare that to rivers, the slopes on rivers are generally very, very low, fractions of a degree. And rivers can also be quite deep. So this is the field for most rivers, and that lies entirely within the regime of subcritical flow. So generally, to add some notation to this, rivers are tranquil, and alluvial fans are generally rapid flow regimes. And as a result of this, because the flows are so rapid, even though they're thinning going down an alluvial fan, they can often carry some very coarse debris. So here's what a modern-day alluvial fan deposit looks like near its head. This is from the surface of the fan. That was the first example I showed you in this presentation at the title. Alluvial fan deposits, because they are really close to steep slopes and deep canyons, can be incredibly coarse, and this sediment, when it's buried and preserved, will become a boulder conglomerate. Now, that boulder probably didn't come down with clear water flow. There's no way that a thin sheet of water could carry that. It may have rolled here just by falling off the slope, which is just a little bit to the right of this photograph. Another way to bring down coarse debris, however, onto a fan surface, particularly a steep gradient one, is through debris flow. And so there are generally three processes that act on alluvial fans to produce the deposits that we see. Two of them are shown here. The first one is debris flow. Debris flow is a mud flow that can carry extremely coarse sediment because it's cohesive and it's dense. They can't flow very far down a low slope, and consequently they're either confined only to the steeper upper parts of the fan surface, or they occur throughout a fan if the fan gradient is steep all the way down. Their deposits are disorganized, really poorly sorted, and often matrix supported, like this one is here. And the only sedimentary structures that may occur could be a crude inverse grading and perhaps long axis imbrication of the class, indicating that they were imbricated in suspension. Debris flow beds pinch out rapidly down slope because of the tendency of a flow like this to freeze rather suddenly at low slopes. And as a matter of fact, with this particular deposit, you follow it down towards the right, I don't know, about 50, 100 meters, and it just ends. The bed just ends because the flow at that point reached a low enough gradient that it simply froze. Very often at the tops of debris flows, you'll have class projecting upward into the bed above them, and that just reflects the fact that they were suspended at the top of the flow, and when the flow froze, they became trapped there. So debris flow deposits tend to build fairly steep alluvial fans, and there are some alluvial fans that are entirely debris flow dominated. Another process that takes place on alluvial fans is something called a sheet flood. Sheet floods are supercritical water flows that can cover most of the fan surface all at once, or at least most of a depositional lobe. They are thin but quite fast, and they're capable of carrying smaller size grades of gravel and all sizes of sand. Their deposits form tabular to lensoidal beds that are often normally graded, reflecting a progressive decrease in the energy of the current as the sheet flood wanes. So carrying gravel at first, and as the flow wanes and slows down, we start depositing sand. Most of the gravel in a sheet flood deposit is carried as bed load and thus is typically well imbricated, like this picture shows and like this photograph shows here. If the sheet flood also carries a lot of sand, then the sand actually may be suspended in the flow and could be deposited above the gravel as almost a separate bed when the flow wanes, and that'll form distinctive gravel-sand couplets that repeat with every flood event. Smaller flood events on alluvial fans and perhaps the waning stages of larger flood events may be characterized by more channelized stream flow. So here are some stream channels coming down some alluvial fan surfaces, and they're erosional all the way down. Most of the fan surface has been entrenched and is inactive, and these flows are depositing all the way down here. So that channel incision produces stream flow on the fan, and each one of those stream channels is a feeder channel for an active fan lobe below it. Deposits in these channels would be less continuous than those in the lobes, and they'd incise into older bedding. So if you looked in this region of the fan, after it's been buried and turned to rock, you would see channels, lots of them, incised into older, more sheet-like deposits. Generally, alluvial fans will tend to build out over time outwards into a basin. And we said earlier that the uppermost parts of a fan will be coarse. The middle parts of the fan would be intermediate, and then the far distal parts of a fan would be, if not fine, at least finer. So as you go down fan, you see this progression from very coarse gravel to fine, perhaps sand, perhaps just finer gravel as you go down. And over time, these facies, as the fan builds out, will migrate out on top of each other. So over time, as this fan continues to build out, we'll continue to build out these zones of coarse, medium, and fine sediment. And as a result, most fan deposits, if you look from the bottom to the top, will coarsen upwards as long as that progradation into the basin continues to take place. Okay, that's it for alluvial fans. The next presentation will be fluvial deposits. Thanks for watching.